Yes. So, in the previous class what we were discussing is that we took your nitrones with your electron deficient alkene, that is your dipolar file, and once we thermally activated we ended up with two products. Okay. One is your coming out of endo approach, another from your exo approach, right. And then we said that not like Diels-Alder reaction, 1,3 dipolar cycloaddition, it is the product which is coming out of less steric indent, that is more favored. That means your endo rule does not work here much better. So, then we said how this steric factor favors your products, exo product. So, we went into endo approach, we said that you can draw the endo approach and we got the endo product. Then after that what we did, we slowly went into your exo approach, okay, in this O minus. So, by two ways we wrote endo way and exo approach, and we found that in exo approach it has been less steric indent. So, exo product tried to be favored, right. Now, what we will see is that why this endo rule is not applicable, it is not applied very good in this. To understand that part, it is we will think Diels-Alder reactions parallelly and we will see why it is not. For example, if I want to do a Diels-Alder reaction, we have a diene and you have your dienophile, right. Same way we think about in our 1,3 dipolar system. So, for example, I have a system like this, just to correlate with your Diels-Alder. Right, I can have a system like this. Now, I am just trying to draw my one-three dipole. Okay. See, I can have a this is what where the bond is formed, right. This is where the bonds are formed. Okay. Apart from that, if you see where there is any interactions, okay, it's mainly this part only have this interaction, if you think about, right. If it is an endo way, this is the endo approach. If I do the same thing for my exo approach, going away. Right. If you can recollect your Diels-Alder reaction, leave the bond formation. Apart from that, in Diels-Alder reaction, if you think about the diene and dipolar, you can have like very good secondary orbital interaction. In this case, if you see in the endo approach, this is the only interaction you can think about. So, you have a minimal secondary overlap. Fine. So, that is the main reason why your endo rule does not apply here. So, it is more now you are going to talk more about your steric one. If it is less steric, then you get major product. Okay. That is where this 1,3 dipolar cycloaddition differs from your Diels-Alder reaction. Clear? In case of exo, that you should remember, important one. Fine. If you are done with this, we will see some reactions. Okay. That means if I for example, I am just taking the similar example. I say that just to understand whether you can write the product. I have a nitrone like that. I can take an alkene. Now, if I ask you to write both the products, can you write? So, NOS, I can have R3, R4, R2, R2 and N R1. So, there is another product I can think about is I can write as 1 with R2 similar to your R4, right. That should be your R3 and R1. So, you can write two products, right. One it's trans of this, another cis. So, this comes out from endo if you write, and this will be from your exo. Okay. Cis comes most of the time from your exo and trans from your endo. Fine. Now, what we will do, now we have like two products like exo and endo, but there are cases where if you take a chiral nitrones, okay, if you take a chiral cyclic nitrone, sometimes you end up with a very sole product, only one product. Okay. For example, I will see this reaction. Take a cyclic chiral nitrones. So, tertiary butyl, okay. I take this cyclic chiral nitrones, okay, and treat it with my electron deficient alkene. See, if I do the thermal activation of this reaction, you end up with only one product, that is this is your nitrogen, okay. Now, you fix your stereochemistry hydrogen over tertiary butyl, and your CO2 CH3, okay. You end up with this only one product. So, why you get this as a single product? If you want to see how they basically interact, that how they come, okay, so that you get only one product, how they come parallelly, you can easily draw them. For example, so this system, I have my hydrogen out, okay, can have my OH, this will be CO2 CH3, fine. Same way I can draw for your nitrone, similar, because this is one which is going to do your dipolar cycloaddition. First you draw that one, fix that part first, then you can have your chirality there, or tertiary butyl with an hydrogen, fine. Now, just look one possibility of coming out, right, like this with your alkene, with your hydrogen out and CO2. That is why you have your hydrogen and CO2 CH3 in the different plane, yeah? And then you have O tertiary beta, just they align like that, fine, and you get this as a sole product. Very interesting working with your cyclic chiral nitrons, like you get only one product. So, you have seen like how you can synthesize nitrons, right, and then you have seen nitrons when it reacts with your electron deficient alkenes, you end up with both the products exo and endo, and you most of the time say that it depends upon your steric rather than endo rule. Then you have seen systems where you can have even chiral cyclic nitrons and you end up with the single products. Okay. That is good. Now, we will the another interesting part is your intramolecular cycloaddition, okay, with your chiral nitrons, that we can just get on. So, we will get your, because this you can this type of reactions you can see lot intramolecular cycloadditions, intramolecular 1,3 dipole cyclo 1,3 dipolar cycloaddition. Yeah, you have studied your Diels-Alder also, right, intramolecular Diels-Alder. So, a cyclic nitron, right. Now, if I do a 1,3 thermally activated, so you end up with a 1,3 dipolar cycloaddition. So, how it happens? If you just want to visualize, see it in a better fashion, like I can draw this. I have a nitrogen, sorry, you have a nitrogen here, you have a double bond, okay. Fine, you can draw this. It's not clear, means I can similarly okay, to be much more clearer. So, you have this system. So, now you have your N plus and O minus. This is now you can do a dipolar cycloaddition. So, what should be your product? So, this is a better way of writing it. So, I can write my nitrogen with this, and then I can write this with my oxygen. So, you get this product. This is your intramolecular 1,3 dipolar cycloaddition reactions. Fine. So, it is only the way you write it. Okay. Let us see one more reaction based on intramolecular. See, this is little bit really interesting one to do on. See, when you are talking about all this chirality, and then it becomes more interesting. If you say this is my OH, okay. Yeah, this is not the real adduct for your or real substrate for your Diels-Alder reaction, okay, because there is no dipolar file or there is no 1,3 dipole. But if I treat it with your hydroxylamine, okay, sodium bicarbonate, now you can see you will get as a very nice intermediate OH. And this part is breakout because you have studied that. Minus see, you will get this because you have studied this reactions, okay, when you do in hydroxylamine. So, it breaks down to give you a nice type of intermediate. This can be a very good intramolecular, this can do your intramolecular 1,3 dipolar cycloaddition, because you have a nitro followed by you have your dipolar file. So, if it does, then what product you end up? I don't know, first I will finish the cyclic ring, because that is an interesting part to be. You have your OH, then this cyclizes, right. This will cyclize, and you have your nitrogen here, and then you have your oxygen, which will have, and then you have N methyl across this, right. Yeah, little bit shifted, and then you have your OH, and your OH, right. So, this is bond here, fine. This is your nitrogen and connected. So, it gets a nice cycloaddition reaction. So, these are very good substrates for doing your intramolecular Diels-Alder reactions, fine. So, that is good. So, we have now seen some important reactions with your cyclic nitrones. We have taken cyclic nitrones, we have taken nitrones, we studied how to synthesize them, we showed them they can do your suprafacial, then we slowly went down and said that exo takes place, less steric, then we studied your chiral nitrones, then we went down and studied about intramolecular Diels-Alder 1,3 dipolar cycloadditions, okay, with your nitrones. Now, what we will do is that we will go to one more another dipole, that is your ozone. I will take ozone 1,3, using ozone as 1,3 dipole, we will study how we can. Basically, structure of ozone, if you want, yeah, you know, guys, know, just to show, just to refresh. This you can be in both the time equilibrium. So, I can have O double bond O plus O minus. So, simply if you draw commonly, it can be done like this, right. That means it should be a structure of ozone, right, which you know very clearly, just to show you. Now, we will see how this undergoes 1,3 dipolar cycloaddition. We will take a simple alkene and see how this chemistry works. Okay, you have this, take an alkene, right. So, what is your first step will be? Your first step will be, right, O minus, and then you attack here and so what is this? This is ozonide type of. So, this see the interesting part now, this is your proper 1,3 cycloaddition, right, dipolar cycloaddition, 1,3 dipolar cycloaddition. Now, what happens, because this is not the product you get when you do ozonolysis of alkene, it undergoes something really interesting one. What is that? You have studied that. See, it undergoes, you can think about making the reverse one. You get a reverse 1,3 cycloaddition. It happens, get reverse 1,3 cycloaddition. Very important. Okay. Once you get reverse cycloaddition, what you will get? You get R carbonyl, okay, plus you will get O minus, O plus carbonyl. So, that is how you split in, okay. That is how it. So, if I write them, so that means what I am getting? I am getting an R carbonyl plus O minus O plus. So, this is not going to recombine like that. It is very hard to recombine like that. What it undergoes, this particular substrate, okay, this acyl radical rotate around 180 degree. So, how you can write then? So, I get R like this plus O minus O plus now you can, now what happens? Again it can undergo 1,3 dipolar cycloaddition, right. So, to give me so this is the product which I got if I take an alkene and do cycloaddition with my ozone, right. You can see very interesting reaction, you see like two normal 1,3 cycloaddition and one reverse 1,3 cycloaddition, the whole process, right. Now, what we will do, see after making this type of ozonides, this ozonolysis workup is much more interesting, because that is not your product, right. So, ozonolysis workup is really interesting part. How you work up ozonolysis normally? Generally, I want to work up ozonolysis. What you use normally? How you work it up? Let's study that. Say I can use dimethyl sulfide, okay, to work. So what I will get if I use dimethyl? I will get an 2 aldehydes, right, and I will get my DMSO. Yeah, zinc is DMSO with dimethyl sulfide. You can use triphenylphosphine. Nowadays, it's very interesting to use triphenylphosphine. If you use triphenylphosphine, same type, you can get 2 aldehydes plus triphenylphosphine oxide. Right. If I work it up using hydrogen peroxide, okay, that also you can do work up. Then you end up with carboxylic acids. See, that's what it becomes. So depending upon your workup, you can get the products you want. Okay. Same way, if I work it up with sodium borohydride, then you end up with 2 alcohols, 2 molecules of alcohol. So you can get up aldehydes, you can end up with an acid, you can end up with an alcohol depending upon your workup. So that's why ozonolysis workup is case important. Fine. Now what we'll do, see, so far we were doing ozonolysis of your linear alkene. If it is a cyclic system, that's you get nice products. If it is cyclic system, for example, you take cyclohexene. If you do ozonolysis in the presence of hydrogen peroxide, what do you end up? Just cyclohexene in the presence of, what do you get? Simple, you get an acid, right, or dicarboxylic acids. See, same cyclohexene. See, I am just to show how the workup. If I treat it in ozone, okay, I am telling the condition in methanol dichloromethane. Second step, I use tosyl. Third step, a little bit of sodium bicarbonate workup with dimethyl sulfide. If I say, what product you can think about? Same cyclohexene type of systems. So you can end up with a nice type of hemiacetal type of systems where one get this. So what happens this reaction? How you end up like this? You want to see the mechanism? How you get that? So nothing but you just, it's a simple. You have your system. You treat it with ozone. Right, you get your ozonide. Then the H plus, it can break up. O positive. Okay, you get this, and then this in, if you have methanol, because you have methanol in the system, right, they can attack again. You have an OMe, then you have OH, two. Okay, then you have methanol, may you have your TSOH, right? That can convert your, because these mechanisms are well known mechanisms. So, you have OMe and then you get your, then if you treat with your dimethyl sulfide, then you end up with your this product. Right? Can get that. Clear. So, depending upon your workup and reagents, you can get your starting with the same substrate, you can end up with an acid, you can end up with an aldehyde. Okay. Another thing, one more example, same with your cyclox, with your bridge. Remember your bridge reduction. If I use lithium in ammonia liquid, right, in tertiary butanol, remember about this proper bridge reduction, right? So, you end up with this one, right. Now, you can treat this with ozone. See, very nice reaction, because you are converting your benzene, so called your anisole, paramethyl substitute anisole. So, if you treat with, you end up with a nice right, you will get this product, because you are treating with ozone. And then if you work it up in the presence of sodium borohydride, okay. So, like that you can play with your workups with your ozone. This is a good synthetic application of your ozone. So, so ozone can be a very good 1,3 dipole. Okay. Now, we will take one more dipole, which is your. So far we were dealing about your allyl anion type of dipoles, okay, which are like bent in structure. Okay. Now, we will see a dipole which is like more linear. That is your propagial type of dipole. So, the one is your nitrile oxide. You can see your nitrile oxides. First, we can get into the synthesis. How we can synthesize your nitrile oxides. Any idea? Same way you taught about your nitrones, you can take your aldehyde, okay, with your, in this case you can think hydroxylamine, aldehyde with your hydroxylamine, right. So, you get a imine type of system. Now, you can use your N-chlorosuccinamide or your chlorine, okay. Fine. So, you can take your chlorine out from here. So, ending up your R H Cl. Fine, and this can then you can to give you R Cl double bond N OH. If you have little bit triethylamine and you do this reaction, then you can get your R, because that can abstract your proton, so creating you O minus with your Cl. This can then leave your Cl, giving you R N plus and O minus. So, can synthesize like this your nitrile oxide. Right? One more method is there for nitrile oxide synthesis. Can you remember? Using your nitro compound, nitro and isocyanate. You can take your nitro compounds, okay, O minus N plus with your cyanate type of compound, phenylized, right? You can, so what will happen? So I will get R CH2 CH2 O minus, and I have my N and phenyl, right? You can get this one, this product. Yes, what this can do now, I can get back and take my hydrogen, fine. So, I might end up with an R H double bond O minus with an N plus, and then my other systems, carbonyl and so NH with a phenyl. Right. So, again I can think of taking this hydrogen out, fine. So, I can take this hydrogen out. So, that will give me my nitrile oxide with, you will have your aniline plus your carbon dioxide. Right, these are two normal ways people use. Okay, one, you can take your aldehyde with your hydroxylamine and create your nitrile oxide, or in another way you can take your nitro compound with your isocyanate type of phenyl isocyanate and end up with your nitrile oxide. So, there are two methods by which you can synthesize them. Any doubt with this? Okay. So, if you see this linear nitrile, because these are linears, they are not like bent. If you see this linear nitrile oxides and do reactions with your alkenes, you end up most of the time stereospecific product. Okay, they maintain stereospecificity. Okay? You can understand from this reaction. You see, I have a trans olefin, Okay. This if I have N-chlorosuccinamide NCS, okay, the presence of little bit amine. So, what I am going to end up? Because you have studied the synthesis, right? So, what you see this compound, okay, if you see the first synthesis of your nitrile oxide, this is your first synthesis of nitrile oxide. See this compound, when you treat it with your chlorine or N-chlorosuccinamide, it ends up with your nitrile oxide. Okay. Same way, this is similar like that, right. Now, I am treating with N-chlorosuccinamide in presence of amine. So, I will end up with my nitrile oxide. Okay. This nitrile oxide then reacts with my alkene, okay, to give me a product. See, I get only one product of this type. Olefins are trans, so I get the trans type of product. Clear? So, that if I take the cis, then what will happen? This is trans olefin I have taken. There are reactions which are done by cis. Cis olefin. This reaction. So, phenyl NCO in triethylamine. So, what I am trying to do here, because I have a nitro compound here, okay, and I have my isocyanate, right, and then in trimer. That means, this is your second synthesis we have studied. So, it will lead to you a nitrile oxide, okay, and that will react with your cis olefin. Then the products you will see is that like this cis type of product. So, that is why this reaction maintains stereospecificity, okay, it is stereospecific this reaction. See, if you see this reaction, it is very interesting in one sense, like if I can, in the presence of hydrogen, nickel, if I and other steps, okay, followed by, if you do this, you end up with a what can be this product, as any idea, like you can think about anywhere you have thought about this product anywhere. No, you can think about your aldol, right. That is right. So, that is that advantage you can bring here, because you take your nitrile oxide, add it to it, and then you just do an hydrogen, the presence of nickel, you end up with an aldol type of thing. This you have just seen in your aldol precursor, right. Okay, that is about the stereospecific of your nitrile oxide. Again, this also has little bit regioselectivity, okay, this nitrile oxide reaction, because you can understand simply in a simple way regioselectivity is there. plus O minus. Okay. Write this way, or okay, your alkyne. I am taking an alkyne, or you can say that plus minus can write this way. So, based on your steric nature, okay, the stereochemistry of these reactions is there, only based on your steric. So, you end up with a nice product. Because of this steric, in this case you have to R here, same product I have written other way around. So, regioselectivity you can get across. You can see this product forming major because it wants to align because of the less steric in nature, right. So, you can pretty well see some sort of regioselectivity also there. Any important applications you can think about this nitrile oxide if you given a choice? Intramolecular cycloaddition, there is one important application which I will teach in this class, but anything you can think about, just one synthesis you can also see that. And this biotin, okay, you can do this biotin synthesis using this type of chemistry. You know biotin because you can label nowadays, it is well known compound in biological systems. That part you can synthesize using your nitrile oxide chemistry, 1,3 dipolar biotin synthesis. That I can, if you want, I can take it in the next class, but even you can biotin synthesis you can get in. Fine. And you have pretty well studied your azide chemistry. Azide undergoes nice click chemistry. If you take an azide and see azide, normally azide chemistry, if you take an azide with an alkene, okay, it is not that much selective, okay. But if you do in copper catalyzed, that is your click chemistry, you get very selective products, right, that you have studied in detail. So, that is more about your 1,3 dipolar cycloaddition reactions. Okay. So, yeah, for example, what I did is that I took like 3 types of dipoles, 2 on base of your allyl type and 1 on propagyl type. Okay. So, to summarize your dipole 1,3 dipole cycloaddition. So, first thing you can think, you can say that this is a proper 4+2 cycloaddition reaction. The second point you want to say is that your 4 pi electron system, you call them as 1,3 dipole, which is similar to your diene. Okay. The second you are saying like 2 pi electron system, which you are talking about is dipolar file. And another thing you have to remember about your 1,3 dipole and your plus dipolar file, most of the case, okay, can be majorly of 3 types it can add, right. We have studied the LUMO and the HOMO, okay. In 3 ways it can add up based on the energy. So, you have type 1 where you have studied about your and you have type 2 and you have type 3. So, you can classify based on their FOMO3 is 3 types, that is just the HOMO of your diene, HOMO of your dipole and the LUMO of your alkene and the other way around, and all the possibilities you have tried, and they can be classified based on 3 types. And if you come back to your 1,3 dipole, your 1,3 dipole can be classified into 2 types, right. One, you have said that it can be allyl anion type, or it should be a propagial or allynyl anion type. So, that is how you can classify your 1,3 dipole. Okay. 2 types, and we have seen several classification based on them. Okay. Allyl anion type, you have lot of ozones and nitro compounds. Propagial, you have seen azides and all these things. And this is your dipolar cells, and you can classify them in 3 types. Another thing you watched upon is that it is suprafacial. It undergoes a suprafacial cycloaddition similar to your Gill-Salder reactions. The main point is that the endo rule does not work here. Okay. The steric factor plays a vital, more about the steric factor, the product determination. Fine. So, these are some important things you have to remember. It falls under 4+2. You have 1,3 dipole, you have dipolar file, 3 types you can classify, and your addition is superficial. Your endo rule does not prevail, it is more with your steric factor. Clear? So, that is how you can simply summarize your 1,3 dipolar cycloaddition. Okay, that is all about 1,3 dipolar cycloaddition. Thanks, guys.